Welcome to this panel discussion today. We're really pleased here at Sofar to host this. It's an incredible topic. Deeply resonates with what we're building here. And just to give you a lay of the land of the surroundings you're in today, as a company, Sofar is building an ocean data intelligence platform to power basically what we believe is a dream of ocean AI. And in the ocean, AI has nothing to do with AI in terms of the challenges. It's about data, information, or the lack thereof. And so super exciting to sit together here and learn about the different perspectives on AI, weather modeling, and we're sort of like in a revolution that transitions away from like a deterministic paradigm of physics-based thinking into like an AI-driven sort of like causality between now and future states. And like everything AI, that's incredibly exciting, like endless opportunities. There are going to be challenges. It's a little bit terrifying, but for the purpose of this discussion, it's mostly incredibly fascinating. So thank you for joining today. I'm looking forward to this discussion and learn from everybody here.
Awesome. Hi, everyone. Thanks for being here. I'm Katie Brigham. I'm a climate tech reporter. I work at Heatmap News, which is a now 2-year-old publication. We just celebrated our 2nd birthday. And yeah, reporting on climate tech, I've gotten to do a good amount of reporting on the intersection of AI and climate. I've talked with folks from Brightband and WindBorne before, who we have representatives from there here today. I think it's a really exciting space. I think obviously AI is very buzzy right now, and there's a lot of climate tech companies, claiming to use AI, but I think which a lot do, obviously, but I think one of the most exciting, convergences of the generative AI and climate space has really been in the weather forecasting space. The models are getting so much better at rapid speeds. There's new ones coming out every month. There's new advances. It's been, just incredibly dynamic and exciting to get to report on this space. And so, I'm very excited that we have 5 experts in the field today that can help us, learn where we're at and how quickly this environment is changing and where we have to go. So I'll let them all quickly introduce themselves. Oh, we have 2 mics, great.
Right. I'm the CEO and co-founder of Sofar Ocean. My name is Janssen. I'm a physical oceanographer by training, so just for my personal resonance with this topic. And that means that basically when we think about weather, I have a slightly different perspective. We as humanity walk on a couple of rocks and a little bit of sand in the middle of the ocean. Our weather and climate system is basically the combination of those 2 big bodies of fluid. And so we have a little bit of bias at the bottom of the atmosphere, but it's important to look at the entire system when we're thinking about weather and climate modeling. This is the 2nd major revolution in weather modeling. Before the Second World War, we were basically doing pattern recognition, like looking at the current state of the atmosphere and then comparing it to the past and figuring out what was going to happen next. In the 1920s, we tried to do physics-based modeling for the first time. It was a complete disaster. Didn't work at all. Didn't stop us from trying. After the Second World War, we got really good at it. So we now have 70 years of hardcore model development based on physics relationships that we numerically integrate. Incredible capability. The dream from the 1920s is far surpassed. What we can do today is absolutely incredible. And now we're at the 2nd revolution, where we basically go back to pattern recognition. But we have a much better tool, which is artificial intelligence. So very excited about this discussion and see where we're at and what we can learn from each other.
Thank you, Tim, and thanks again to you and your team here at Sofar for having us here today. And it's so nice that so many of you are making us feel like AI weather isn't a weird thing, and that we're excited that you're excited. So I'm Julian Green. I'm the CEO of Brightband, and my co-founders, since I am from the AI side, this is my 6th startup and my 3rd AI startup, but know basically nothing about weather. So have partnered with Ryan Kiesler on the AI side, who wrote a great paper in 2022, sort of for the first time showing that AI could forecast the weather as well as the physics, numerical weather prediction. And then with Daniel Rothenberg, who is a meteorologist and was at Tomorrow.io and Waymo and other places, has been involved in weather data for a long time. And so Brightband's approach is try and get some really good people from AI and from weather data and try and solve the problems of AI weather forecasting. And we believe that going directly from observations and the much larger amounts of data that are available than are currently being used by the forecasting systems should hopefully improve our ability to forecast. So that's me, and I'll pass it to Karthik.
Thank you. I'm Karthik. I'm a scientist and engineer at NVIDIA. Thanks, Julian, for organizing this great panel. It is a very exciting time for AI and weather forecasting, and I'm part of the Earth-2 initiative at NVIDIA, which has been one of the forerunners in this space, along with Ryan's work in 2022. We developed one of the first AI models for predicting the weather at fairly coarse resolutions, and since then, we've been on this journey towards using generative AI to get to ever higher resolutions that are relevant to humans and ecosystems. Very excited about all the other developments in the sort of digital twinning space as well, which is bringing all of this information to people's fingertips and helping with decision making. So excited to talk about some of that today. Thanks.
Hi, everyone. I'm Stephan Hoyer. Really great to be here with this wonderful panel. So I'm a research lead at Google, and where I've been for, I guess, about 9 years now, and working at the sort of intersection of AI and the physical sciences. And for about the past 4 years or so, I've been working on global weather and climate modeling. So my team showed we have a global model called Neural GCM that is it's a hybrid approach that combines we have a physics simulator and AI components that we kind of all put together in an AI framework. And we were able to get that model to show one of the first models to show better results than to the conventional physics-based models for both ensemble weather forecasting and for some early sort of atmosphere-only climate simulations. So that was in a paper that we published in Nature last year. And so kind of continuing to work in this space and really excited about the potential, I think especially currently, especially in the direction of climate. I think that AI could be a really powerful tool here, combined with physical models.
Thanks. I am Joan Creus-Costa, and co-founder and now leading AI at WindBorne Systems. First of all, thank you so much for hosting this event and inviting us here. It's also like a pleasure to be surrounded by a lot of experts that I only previously knew through archive. Yeah, at WindBorne, we started as a weather balloon company. So came out of a student project, and we built weather balloons that fly over the world, and they collect data where right now there's big data gaps. So say over the oceans, we do not have direct measurements. In the Southern Hemisphere, we're also like missing a lot of measurements. And so our mission started with, we're going to make balloons that fly for weeks and months instead of hours, and fill in those gaps. For the past couple of years, we've also been doing work on the modeling front, and building our own like deep learning forecasts for weather. And we're continuing to do a lot of work here. And yeah, very exciting to chat about it with everyone else here.
All right, awesome. Let's kick it off. And these questions are going to be relatively open-ended, not directed towards anyone in particular. So, pass the mic or use your outside voice, I guess, as you answer. But I guess one of the main things we want to touch on is at this moment, can we truly say that AI weather prediction models are better than the numerical weather prediction models? Those are the physics-based models used by entities like the National Weather Service. And perhaps more importantly, what are the metrics by which we're measuring performance, and which performance is actually exceeding another?
You want to start?
Sure, I'll start. I've been involved in a few weather benchmarking projects. So I think today we can say, I think pretty indisputably that for the large scale weather patterns, so global scale weather, and that means sort of large, that we're doing it better with AI. And so that means that's kind of the key weather patterns for predicting the weather up to like a few weeks in advance, and kind of like what a meteorologist would kind of show on TV. So kind of like big weather patterns, like there's a high pressure system like over here. There's like a tropical cyclone coming in. I think I think that's the place where so far the AI models are pretty compelling. But where they aren't yet, I would say, is at the small scales. So resolving the details like And here it's just more a mixed bag, like saying like exactly is it how windy is it going to be on a sailboat in the San Francisco Bay, for example. That's harder to say.
And I've got
I think on the, I'll add to that. I think it's interesting. I think you're right in the sense that the metrics is the big challenge. Like to say a model is better than another one, it's, depends on how you look at it. So if you think about traditional model development, there's two layers in that development. One is basically the model developers who ensure that basically basic properties like conservation of mass, momentum, energy, and the distribution of energy across different length scales is sort of like met before it goes to a forecaster. And then a forecaster has basically a more sort of like intuitive, metrics around like, is this a skillful forecast? Does it actually match to reality? Because at that level, you don't have to worry about the other parts anymore because that was taken care before. And so I think on the forecast level, we've looked at like metrics of like whether AI is better than sort of like traditional models, and generally they do better. Also because they're generally trained on those metrics and they will outperform the models at a fraction of the cost from the compute. I think the challenges are more around like the underlying sort of like physics, is that properly represented? And why that matters is, for instance, on the statistics and the uncertainty of weather. Like you need to have certain properties of the model to behave in a certain way to get, for instance, if you do a large ensemble of realizations to get the proper statistic. And this is really a fundamental thing for a chaotic system like weather to understand the statistics. And in fact, I think AI is one of the major advantages there is that we can build realizations like at will because they're almost free. So we can do thousands of realizations, get great statistics, but the statistical spread has to be right. And I think that's still a place where there's a lot of work to be done. But again, the opportunity is incredible. And to take it one step level on sort of like the sort of like local stuff, I agree that sort of like the regional stuff is going to be a challenge today with AI. I think there is an opportunity to like think about hyperlocal, directly data-driven forecasting, where I think AI is going to be spectacular, right out of the box today. And I think so there is like, if you think about the different skills, global, I think there's a challenge there from like model developer to forecasting. Which metrics are we using? Are we getting sort of like the basics of the model right? That's, I think, still work in progress. Regional, there's a challenge just from a resolution perspective and a data perspective. Hyperlocal, I think the opportunities today, and it's going to be, I think, incredible.
So I agree with all that, and to try and put numbers on that, and I think the highest resolution large AI models are at 0.25 degrees, which is 25K at the equator, and so that's the resolution currently, and there's obviously opportunities to go higher resolution. At that resolution, if you look at WeatherBench, which is a Google research way of measuring the global errors, the root mean square error of a bunch of the different weather-related metrics, so temperature and wind speed and so on. If you look at that 7 days out, GraphCast as an example is doing 3 degrees better on temperature and 9 meters per second better on wind 7 days out than the best numerical weather prediction model, physics model, which is the ECMWF's IFS high-res model. So that's sort of the order of improvement. And we've really gone from, a few years ago, AI was not as good as the numerical weather prediction to one where, at least on, as described on, large feature global basis, it is now better, more accurate. It may be having more predictability at longer lead times, which is super exciting. And it's way faster and way cheaper.
Just a very quick sort of comment on what Tim said. I think we're also finding that these models are starting to learn the physics in ways that we did not expect, even though they're completely trained on data. So some of the work, for example, from UW, that's showing that these models are behaving in sort of having the wave dynamics that we expect, even though we're not encoding any of the physics, any of the Navier-Stokes or physics into it.
No, just a very good comment, agreeing with what everyone has said. But yeah, in the end, one other thing is that it can be sometimes hard to compare physics-based models to AI models. And again, like work like WeatherBench is extremely useful in comparing those two because, a lot of it comes down to like, how do you train your model? If you train your model against another aggressive objective, you will get something that's a bit like an ensemble, and it will be blurry. And that's a very common thing that we find with AI models. And there's ways to measure it. You've done a lot of work with weather bench and the energy spectra. But in the end, like, it boils down to like what are you optimizing for? And if you optimize for something that results in something that's a bit like an ensemble, you will get that, and it will be a bit more blurry. If there's also been work on more diffusion-based models where you get higher resolution. So there's wide range of things here, and yeah, when comparing to physical models, it's very important to not just like think like, oh, there are like a 10% worse. That means that like physics-based models are over. There is a lot of nuance here, and it's very good that the community is aware of that and tries to get the best possible model under this.
So just one thing, just for the whole room, like there's a lot of experts here, but I'm sure there's also maybe people that are not that expert on this, this topic. A simple way to like think about like what the importance of metrics is. For instance, if you score a model on an RMS error, like a root mean square error, you can score really high yet not have a real forecast. The best way to like score really high on a root mean square error is to kind of blur out the edges. And so this is one of the challenges with metrics. So if you have the wrong metric, you can like perform really well and scream from the roofs of like, we did it, we broke all the records. But in reality, you don't have an operational model yet. So this is the challenge around like the complexity of the metrics has to be sufficient to capture the actual performance that you need the model to have to deliver what it needs to do operationally.
So on that, we've tried to produce an open thing called Extreme Weather Bench, sort of inspired by Weather Bench. And instead of global sort of errors, it tries to look at case studies. So let's look at the 10 biggest hurricanes. Let's look at the 10 biggest wildfires. Let's look at the 10 biggest floods, and then compare how models did on forecasting that to try and get to a measure of more. Is it a useful, opinionated local forecast? Because we're all here. None of us is at the global average temperature, right? We're all at the temperature we have here. So we're trying to start to think about how to do that, and it's a big problem. And obviously, you sort of want to measure every individual's weather everywhere in the world and see how accurate forecast models are for that. But that's obviously sort of a hard problem. So we need more work done on metrics.
Stephan wants to say something.
Katie's only going to get one question.
It's all good. The hope is that you kind of use them as jumping off points. So on that note, obviously, most of the AI-based models now still rely on, taking initial conditions and doing their training based on the physics-based models. In that sense, you're not even really saving on compute costs if you still rely on the physics-based models, and it's not really end-to-end AI. Perhaps that's arguable, Julian. But I'm curious when you guys think we can get to a point where we can just turn the physics-based models off. Are we nearing that future, or will we be reliant on them for some time to come?
Stephan should definitely talk about this, and Karthik should definitely talk about this. Let me do one thing. Let me do one thing real quick. Is when you talk about what AI is doing currently, I think it's important to understand, and many may already know this, but there's sort of two parts to current forecasting. There's taking all the sparse observations that have gaps, they're sparse in time and space, and doing what's called data assimilation to get them into sort of a homogenized, uniform, three-dimensional grid of the world. And from that, the models forecast. And so data assimilation and forecasting. So current AI has gone from that intermediate step, the sort of assimilated step. And so you're saving, energy-wise on the comparison between, inference, training and then inference costs for AI models doing forecasting versus NWP. And those are non-trivial, right? So, the UK recently bought $1 billion supercomputer to do their weather forecasting, and it runs on tens of megawatts, and it's, CPU Fortran, and Karthik's going to be giving away GPUs later, by the way. But it's 6 orders of magnitude more compute efficient. So there's some efficiencies there. To your point, we still rely upon that first step of data assimilation. What we're trying to do at Brightband and others, I think also, is to go back to the raw observations. So you can skip that expensive data assimilation step and deal with the messiness of having sparse observations. And then we will have an end-to-end AI thing that we can turn arbitrarily quickly and do lots of exciting things with, including even taking in custom observations and giving out a custom forecast. So that's the dream.
Yeah, a couple of quick comments. We already have actually AI-based data simulation working right now. Whether it's operational is a different question, but the concept has been proven, and we've got AIDA. ECMWF has got AIFS right now, which is maybe 2 years behind the first AI models that came out in the space. So we should expect in, say, a year and a half, ECMWF would have AIDA as well. And would they turn off IFS? Probably not, but they would have an end-to-end AI forecasting system in a year or two. That's my bet.
Just maybe a couple of comments. I mean, I guess so first of all, I don't see like a really firm line between the physics models and the AI models. I think it's all sort of a spectrum, and there are a lot of nice, like half the nice features of the AI models is like it's not written in Fortran, it runs on GPUs, it's written in a modern programming language, and you can include physics-based components in there. And so I don't think that's terrible necessarily to be using physics-based models as sort of part of the approach. And then I'll also say that for some applications, I think climate modeling would be one good example of this. We already don't really need like the initial conditions part's a very, very small part of climate modeling. So you're already seeing that you could, and of course there are a lot of, we haven't built full AI climate models yet. That'll be coming in probably over the next couple of years as we kind of figure out how to model other parts of the Earth system beyond the atmosphere, like the oceans and so forth. But when we have those models, will I think just like we kind of already kind of like see pretty clearly how we can just run the AI models sort of all on their own and get like very large, like million-fold sort of speed ups over physics-based models for climate.
Yeah. And yeah, at WindBorne, we're people based on observations, obviously, like we think they are very important, but at the same time, I do think there is still immense value in those gridded data sets. So for training, for instance, your gradients are going to be a lot nicer and lower noise if you train off, a very dense gridded data set compared to sparse observations. In the end, like we think that you will still want that. It helps you a lot. But to like push the limits, you will want observations and start getting away from good data sets. Ourselves, we are also doing a lot of research on, can we do DA without physics-based models? And we have promising results internally that we hope to share soon. So we will start seeing a lot more of, doing things from raw observations, but that doesn't mean that, the existing data sets are useless. They're still insanely useful. In real time, we obviously want to be doing more things from observations because it reduces latency, it improves resolution. But again, like all of that is coupled with improvements that also go in physics. Yeah.
Yeah, and just a last note, I don't think there is a fundamental reason why we can't do it all, and there is no fundamental reason why eventually we can't turn off physics-based modeling. It's also not the goal. And Stephan, to your point, in this problem, you kind of have your cake and eat it. You can have, all the benefits of like what you would get in an AI model around like the ability to like run more efficiently on GPUs and have physics in there if you want to. And the goal is not to get rid of physics, I hope. The goal is to like have a more efficient model that would mimic the same sort of like, understanding of the physical world as our physics-based models sort of like represent. And whether that's going to be pure AI and whether that's today, tomorrow, a year from now or years from now, or some sort of hybrid model is sort of like irrelevant. I think the opportunity is just to like, take for what it is that you need it for today and how operational do you need to have it today. Look, if artificial intelligent forecast models today were better than operational forecast models that were much more expensive, we would turn them off. So clearly that's not the case yet for whatever reason. And if that does happen, then eventually we'll work towards like turning them off one way or the other. And I think the future right now probably is hybrid, like where you have physics baked into like, the benefits of having AI in there. And I'd love to be proven wrong in like 6 months or so. And that'd be a wonderful future for all of us.
Awesome. Thanks, you guys. And I'm wondering, what are the tangible ways that normal people will kind of experience the benefits of AI-based weather forecasting? Like, will it be that the 7-day weather forecast is much more accurate than it is today? That if it says it's going to rain in 2 hours, it's actually going to rain definitely in 2 hours? I guess another way of thinking about this is sort of like, what can we predict with AI-based weather models that we can't really predict with much accuracy today?
So ultimately, I think the accuracy is going to rely on data. Like more than ever, I think data-driven models require data. So the more data, we get better accuracy. I think the really exciting thing is the low cost and the speed with which you can do computation. You can run it on demand. Like most any forecast you look at is old because we only run them once in a while because they're pretty expensive. You could run this on demand anytime to bring in the latest information you have, do data assimilation, bring the model up to par with what we know right now, because it's a challenge of forecasting, right? As soon as we move away from now, we don't have observations anymore. So we're going to have to figure out the relationships between now and the future. The closer we can do the forecast to now, to where you want to know the answer, the closer you're going to be able to like predict the near-term future state. And if the computation is free, then you can do that anytime, and that's going to be, I think, incredibly exciting.
Yeah, I agree. I mean, you sort of have this new tool which gives you way more capability, and it can be used in a bunch of different areas. So we've talked about extending the lead time out. We've talked about more data, hopefully bringing more accuracy. I tend to think that the thing people haven't got their heads around is how currently we're in this every 6 hours, and you get the benchmark government approved weather forecast at a grid point, not where you are, but somewhere near you, and you hope that that's relevant, right? And instead, we're moving to a situation where you can run a forecast at any time for any location and outputting the thing you care about, which is rarely, temperature or wind speed or it's more some derived variable. It's, should I take my umbrella out today? Is soccer on? Is the energy price going to go up or down based upon how much renewable energy is going to be supplied and how much the heat or cool is going to change, the demand? These are the things people make decisions about. And I think a full AI end-to-end system allows you to output what you want rather than these intermediate sort of hints towards what you want, which is traditionally the way people think about weather.
Yeah, I think one dimension that I think, Tim, you mentioned early on was the speed of these models. And that really changes the game, even if the accuracy is exactly the same as a numerical model. And you could run these models to generate, 10,000 member ensembles, which are key to sort of discover the needle in the haystack, very rare events that you just couldn't, predict with numerical models that you couldn't afford to run for anything more than, say, a 50-member ensemble. So I think that's really where, at least at this stage, AI can make a big difference, is in being able to characterize these low likelihood, high impact events.
So I'll say something a little controversial. So we've been in AI weather modeling, we've been pretty focused on sort of global weather forecasting and like forecasting over the next week or two. And honestly, the main reason for that is because that's like the place where physics-based models are the best. They're like the best baseline. We have like the best baseline models. We have the best metrics, most reliable sort of assessments. We could say like, look, we solved like this problem that is like the canonical problem of weather forecasting, and we could say we could prove that we're better. But the AI models are not that much better. I think if you look at like the metrics, if you compare to like the ensemble forecasts, in the best case scenario for like a 1 week forecast, it's like your AI models are maybe 10, maybe 20% better on most metrics. And that like a lead time difference is like maybe something like maybe you get your 1 week weather forecasts maybe 12 hours in advance of what you could get it today with the physics-based models. That's not that compelling. And honestly, I think it's going to be hard to improve on that a lot more just because of the chaotic nature of weather prediction. But I will mention one area where I think that there's other areas are probably going to have more potential. And I think one that I think we've already seen actually is if you, like some of my colleagues at Google have worked on, is if you look at like local like rainfall modeling, or like is it going to rain here in the next hour from now? If you type in your location in Google search, it's like already like running live today. You can see like a sort of a nowcast based model that's used AI and is way better than any of the old school sort of physics based approaches for like local scale modeling. That's mostly because local scale modeling is just a much harder problem. So that the baselines were worse. So I think we need to kind of look beyond benchmarks and look more like real world use cases to find the opportunities for AI.
Echoing all the points, especially the one about helping us with probabilistic forecasts and allowing for like very large ensembles. That's something where I think like there's like a big edge here. Similarly, like things like MapNet are really good models for local forecasting. It's very cool that they're live already. And like you can really see a big difference there. And yeah, another one for concrete examples. One, it's more of a trivia thing more than like, a general thing, but something that a lot of people have noticed is deep learning forecasts tend to be better at hurricane prediction, which is something that, is very important for society. The reason why, there's a bunch of theories, but maybe the fact that you have, some like tabula rasa and you don't have any, constraints that the physics model might have means that it just predicts some intensification better or the tracks. So that's one where for this specific thing, we've seen it in our models, but other models have seen the same phenomena where it happens to be quite good at that and predicting tracks. And obviously predicting tracks of hurricanes is extremely important for society. And that's very cool that this is not we are, maybe 5% better at 2 meter temperature, which might be maybe meaningless to someone because, maybe it's just blur. But, the fact that like hurricane tracks are better is something that constantly makes me very happy.
Awesome. And I'm wondering, from all of you, again, what technologies you're personally most excited about that you think can lead to advancements in the AI weather prediction space? And that could be, new ways of gathering data, advancements in chip speeds, new ways of running the models themselves, whatever it may be.
Oh, I guess I can take it. Yeah, so for one, I would love to have a chat with Karthik after and try to get hold of some GPUs. We started with gaming GPUs and we have moved on to much bigger server GPUs, which has been great for doing more modeling. So obviously that's always a good one. Sorry, I totally back the what improvements are
cool technologies that you're excited about.
Oh yeah, so obviously, yeah, improvements in compute speed are one. And then another one that we're very excited about is using more observations, both in training and inference. So one is if you use observations in training, you can get higher resolution models compared to something that might be trained off the 15 miles of ERA5. And also when you're making forecasts, a lot of it will be based on your initial conditions. In the end, like physics models are quite good at propagating physics. When you compare the European model or the American model, a big difference is how you initialize it. And so, increasing the observation density and being able to use that in AI models with AI-based data simulation is something that we also think will make a big impact.
All right, I'll give my really dorky answer, which is that we need to work on better tools working with data. So the biggest challenge is this is like AI weather modeling is like a canonical big data problem. We've worked with data sets that are like literally a petabyte of data, and like the tooling it's gotten much better, I will say. And some of you in the audience have worked on that. So like file formats like ZAR and sort of other tools for processing data. And I think that practically speaking, that if we improve those tools, that'll have a big impact on the speed of research.
There's too many to choose from, but I'll just pick one sort of at random. I think generative AI is offering lots of opportunities to get to hyperlocal scale, sort of the problems that Stephan talked about, but also using super resolution diffusion modeling to essentially replace a lot of the techniques that have been developed in the past. That's one area that I'm very excited about. Also useful for data assimilation, data fusion. So it seems like sort of the Swiss Army knife that can tackle lots of different problems in the NWP workspace. Won't get to hardware just yet.
So on the data side, I think there's a technology problem, but I also think there's a sort of business model and organization problem. I think, the world in which governments did everything, and you had government satellites, and you had government data pipelines, and government forecasting, and government forecasts. If we move to this world where anyone can run an AI forecast model, the big question is, how do you pipe the world's observations to everybody who wants to run a forecast model? And that is a different technology problem to solve, and it's a different organizational and, dare I say, political problem as well. And we need to think about how that works, and it becomes more of a streaming architecture rather than a batch every 6 hour architecture. We have observations coming in all the time. We want to be able to see what effect those have on the things that we care about in real time.
Yeah, I think everybody here would agree that as a modeler right now, you're like a kid in a candy store. Like it's like so many cool things happening. It's hard to like figure out like which one you like best, and it might switch from week to week. So that part is like to decide. There's just like too much to choose from. Almost. I think the going what Julian was pointing at. This is sort of like also where I come from mostly. Walter Munk was a renowned oceanographer who in the 1970s said basically, and look, he loved theory, like had a really good understanding of physics, definitely. But he said like, look, the real problem is sampling, and sampling, and it's a mundane effort in many ways, but ultimately the quality of your model is going to rely on how well you can initiate it, and it doesn't really matter what you use. Eventually, we will all have, and we all already have today. We all have access to the same models, like everybody does. NOAA does, ECMWF does, and the differences in the quality and the fidelity of those models is really how much and how they put the data into that initial condition. So that paradigm around like, getting data, getting better at data, scaling data acquisition hasn't changed fundamentally. The cool thing is that we now have the capabilities and the models to translate that information much more efficiently and effectively into like what the future state of this environment is going to look like. But it doesn't, I think, preclude the necessity to think about more dynamic data assimilation strategies, like the availability of data from everyone, and redefine like what forecasting is actually going to look like, both from a technical and a business perspective. If companies like ours are going to do forecasting, then that is a completely new thing that wasn't possible 5 years ago, simply because the cost would be outrageous and you wouldn't have the data to make it worth your while. Because the only reason why you want to run a separate forecast is because you have more data, a better way of doing data assimilation of some advantage otherwise. But ultimately comes back, I think, to an information advantage. So there's a lot of rethinking to do on that side. But I think, again, it's an incredibly exciting future. There are going to be some challenges, among which the political one. So I'll leave it at that.
Yeah, and that kind of gets into my next question, which is who stands to benefit most? Like, what industries stand to benefit most from these newer, more accurate AI weather forecasts? Like, who are the customers for this, and how are we going to see that play out in various industries?
Literally everyone. Every industry in the world is impacted by its environment, one way or the other, either through a supply chain dependency or directly. For instance, we built Wayfinder, which is a routing platform like Google Maps for the ocean for large commercial ships. If you run a ship in the ocean, you're ultimately dependent on weather there. But if you're a factory in the middle of the United States, you're probably going to get part of your supply chain from that ship that was driving in the ocean. So indirectly, you're going to be impacted as well. And so I think from a consumer to every major industry in the world, weather dependencies might be quantified in a different way, like the value to, and the dependency and the reliability on their, the impact of like uncertainty in weather could be larger from one to the other, but ultimately everybody does. And then going back to like the idea of being able to run large ensembles and understanding the uncertainty of weather, it is mostly the uncertainty that costs a lot of money. And it's the part that we can solve for. We can't solve for weather. We can't technically change it, right? It is what it is. But understanding like the uncertainty of that weather will allow you to make incrementally better decisions. And that is incredibly valuable for every industry impacting and operating in the environment, which is everyone.
So I think there's people who currently use weather forecasting, and those are distributed across many different areas, government, military, and then a bunch of industrial folks. Obviously, energy is a big one, agriculture, insurance, supply chain, transportation. I think there's a lot of people who should use weather forecasting who don't, and I think that's an exciting area. A lot of people, if you go to Edgar's, the SEC Edgar's database, and you look up which words people use as reasons for why their results were different than were expected, weather and climate are the number one external factor, not politics, not war, not other things. And yet, comparatively few people use weather in an intelligent way to inform their decisions, and uncertainty clearly plays into that. Companies spend about $7 billion a year on forecasting. Governments spend about $35 billion a year. Just one area of improved weather, so for extreme weather events, if you were able to have an earlier indication of where a hurricane's going to be, and other extreme weather, that would, the World Bank estimates we would save $162 billion a year in saved lives and assets that we could have safeguarded against that extreme weather. So I think there's massive underinvestment in weather currently. We've got a great new tool that makes it better for everyone. And so I agree. I think all the people who currently use forecasting are going to be more happier. And I think everyone who should be using weather forecasting and isn't is going to be happier.
Yeah, not much to add, but yeah, everyone stands to benefit from better weather forecasts. Some industries like aviation are obviously very well equipped to adapt to changes in the AI NWB space, but there's way too many others that don't quite have the expertise right now. And I think translating weather forecasts into useful decision-making tools is probably a gap that needs to be filled for many industries.
I'll just mention one area that I'm excited about, which is, I think, potentially dramatically improving climate forecasts and sort of making it comes a better understanding of the impacts of climate change for adaptation. I think that AI has a lot of potential there.
Yeah, and I think it's a mix of in terms of like who's going to benefit. Obviously, everyone's going to benefit. Another question is who's going to benefit first, and it's going to be the people who maybe like care most about specific things. So, for instance, myself, if the forecast is like 1 degree better, I probably will not change anything, and it doesn't matter as much to me. A hurricane track forecast being better, that actually probably matters quite a bit to me. The probability of a cold snap in Texas being 1%, it might matter to me if I'm, doing like options trading of, energy prices. So, it depends on what you care about. And obviously, if you're positioned to care about something in particular, you will switch faster. For instance, for navigating balloons, we see a lot more accurate forecasting if you use our internal models. So we've switched to that because, we also like dog food our models. So it's a mix of, are you ready to switch? And can you see the benefits of the switch? And for some things, the answer is yes right now. Like maybe hurricanes, maybe like upper level winds. For other things, it might be like, we can wait until it gets really better.
Great. And before we jump into some audience questions, I just wanted to ask quickly, as it's super relevant to this week. Will using AI to predict the weather, will that lead to a lot less energy usage in terms of, how much energy we're consuming predicting the weather overall? And, by what order of magnitude? How much could it impact that?
I'm sure that someone else here will have exact numbers, but the answer is that it might be shocking because normally when we think about AI, we think about like, oh, it uses, data centers worth of electricity and, it uses a lot of power. But in the case of weather forecasting, it's actually like the opposite, which is maybe not intuitive. But when you run physics-based models, which, amazing pieces of engineering that have evolved over many decades and are just marvel, they, use like 10,000 CPUs running for like, continuously to predict the weather. And that's really expensive and also use a lot of power and, with that CO2. When you look at deep learning models, you are able to take advantage of how efficient GPUs are at matrix multiplication. And you end up with models that, perform better on RMS that you can run on, probably your like laptop GPU, which obviously uses a lot like less power. Now that's great news for everyone. And it also means that you can like, scale up the deep learning weather forecasting power by a factor of 10 or a factor of 100. And we would love to do that and still come out ahead while providing much better forecasts. So it just lets you do a different trade-off.
About 2 years ago, when we measured the performance of our ForecastNet model, and it's similar to many other models out there, it was about 3,000 times more energy efficient on GPUs versus the numerical models running on CPUs. With the generative AI models today, it's about 10,000 times more energy efficient than numerical models. Of course, that's just the forecasting. We're yet to see that happen in DA and other spaces, but we should expect similar numbers.
All right, I'll I'll attempt to be controversial. It's way more efficient using AI, but I think it's going to be so great, we're going to use a lot of it. And I think that's the sort of the economics answer. Now, it may save us a lot of energy in, not wasted transportation journeys, or plane and ship related efficiencies. And there's going to be other ways that it will be better overall. But inevitably, when you get an amazing new tool, you end up wanting to use it a lot.
Yeah, it's like, we thought we were going to use less paper when we had printers and computers, and that didn't work either. So yeah, absolutely. I think it doesn't matter though. Like, I don't know the answer. I've absolutely no idea whether we're going to use less or more. I think it'll probably be more. I think with the idea of like playing with a new tool and everybody building their own model, training it, etc. But it's in the noise, and the impact of improvements to forecastability and reduction of uncertainty in weather is going to be incredible. Like in terms of like the potential savings, and not just economic, but also from an emissions perspective, like the diversions you don't have to take with a truck, or with a ship, or an airplane. It's going to be net positive for sure. The costs and even the emissions associated with weather forecasting, like for instance today, like maybe there's a handful of like operational forecast centers that really run continuous forecast. I mean, take the complete emission contributions to that. I don't think it's going to be meaningful compared to what you would benefit from improving that, even if you end up spending a little bit more on emissions. So I think in a narrow space, in a narrow sort of sense of the word, I don't know the answer, and I don't suspect it's going to be great. But in the broader sense, I think it's going to be an amazing outcome from a sort of like climate impact perspective.
Awesome. We can open it up.
Hey, quick question. I'm Joan. And walking over here, I saw a big NOAA vessel that was either loading or unloading what looked like some ocean measurement instrumentation. And you talked about greater adoption of these models. So I have a question around how public-private economics evolve, in a different landscape of funding of NOAA. And similarly, you mentioned some of the uses tied to corporates, for example, and how few corporates, maybe I'm sharing a bias, but how few corporates effectively use weather data to inform, CapEx, whatever, operations planning, supply chain planning. So how do you see public-private and then B2B economic models changing, if any, to really see the full potential and the full impact that these weather models can have?
I'll take the first step. Look, I think public-private partnerships are incredibly important to drive advances in spaces like this. And I'll talk from the ocean narrative. We have a massive data gap to fill there, like a truly spectacular data gap. Without sort of like strong public-private partnerships, I don't think we can succeed there. Like, that being said, I think there is a strong complementary sort of like drive between what industry, like most of us, can do together with government. The government mandate is to serve the public, right? It doesn't matter what it costs. We as a society pay for that because they deliver services that we all agree on, or maybe not all, but at least some of us agree on that we would need. We as companies need to derive direct value of the products that we deliver. That's a completely different motion, right? But as a result, we're highly incentivized to work very efficient and deploy the latest technologies to drive that efficiency. And in that sense, I think we can help and complement government partners to deliver better products to the public, which is part of what they're trying to achieve. So I think the potential of working together is more important than ever. But it also requires, and this goes maybe sort of like opposite to like where that might be driving toward, that we need to make sure that organizations like NOAA are funded, are made capable of being a strong partner in that relationship. And so from the perspective of, say, the United States, if we want to lead in ocean and weather modeling, period, then we don't have a choice but to make sure that those public partners are available to de-risk technology and to help create markets that private companies like ours will need to be able to operate and to unlock private capital to be invested in it. So that way, basically, we can scale things up and ramp it up really effectively. And so I think hopefully that answers part of your question. I'll hand it off to Julian, who probably has more to say on that.
I think it's a fascinating question, right? You've gone from a world in which basically governments did everything, And so clearly it's going to be more commercial involvement. And what you want, and the market will drive this, is you want different organizations to do what they're good at. I don't particularly want to be told whether to evacuate San Francisco by a private company, right? I think that probably should come from the government. But if I want lots of new technology built really quickly using private capital, then I want, you know, a lot of people throwing a lot of stuff against the wall. And so, you know, there are some really interesting questions around, you know, once we have a lot of commercial sensing networks, you know, can we roll that together so there's one place where you can get all the weather data, or is it inevitably going to be super fragmented and did this nice world in which the government and the US is committed to being open with their weather data, which is amazing and has enabled a lot of the innovation you're seeing today. You know, what happens when there's a bunch of, you know, commercial sensing networks? How does the licensing work? You know, they've got to pay for the sensing networks, but you also want that data shared at some level. So there's a bunch of things as we move from a fully government to a government and lots of commercial innovation world that need to be solved.
Well, and you have in between like watch duty, there are, you know, non-profits and sort of sit in between as well, just for the use case that you mentioned.
Yes.
Any comments?
I don't want to like take up the question. Yeah.
All right, someone else?
Hey, given that a lot of the data that you guys use come from government agencies, I was curious if you can speak of if there is a prime example of a particular country or government that does it particularly well. Like, this is a shining example, house on the hill, we should all adapt to the standard of this country. And conversely, are there difficulties in scaling this technology to places where you have lack of observational data because their government may not have the same array of sensors everywhere?
Can you take some of it?
Yeah, I'll just make a quick comment that a lot of the work that was developed in the last few years has been using this data set called ERA5, which came from ECMWF, which is sort of the leading numerical weather forecasting agency. Of course, there's lots of data sets out there for regional, much finer resolution weather data, et cetera. But it is definitely a gap in certain countries where you just don't have high quality data to train on. So you have to sort of transfer from one region to another and fine tune on other data sets.
That's about data and a sensor problem, it sounds like, not just
Right.
data problem.
So we should celebrate one thing, which is actually countries have collaborated in the past on weather data really quite well. This is one of the few examples of scientific, you know, collaboration. The WMO runs a system where all the sort of approved Met Office countries share all of their information. And the US has done an amazing job of making the data, both the observation data and the product of forecasts available to people. And ECMWF has been very leading European collaboration. The scary and sad thing, if you look at how the world is observed and who weather models are built for, is that if you live in a poor country, as defined by the World Bank, then your 1 day forecast is as bad as a rich country's 7 day forecast, right? And you can probably imagine how much you rely upon a 7 day forecast here. That's how people in poor countries think about the weather tomorrow. And they have less capability to withstand if you're a farmer in Pakistan and you're wondering when the monsoon's going to happen. A bad day could mean that your crops and livelihood are wiped out. They have less ability to withstand weather-related crises. So that is something we all need to work on. And there have been attempts to invest in more observations in poor countries. And we also need to develop models that work well for them. And I know a lot of people are trying to do that.
Yeah, the problem is non-local. I mean, there's also places in the world where there's nobody, and we still need information there because that information is going to propagate across the globe to somewhere else. And so it's not just we can say like, well, you're a poor country, so we don't really have to care about that. That information is also going to impact our forecast. So to truly be better, this is a global problem. This is not something you can sort of like bring down to like countries. I think the challenge ahead is how do we leverage commercial sensor networks? Because that is sort of like a new phenomenon. And this started out in space where you could have, breaking away from like government-owned, large satellites to like distributed sensor networks with CubeSats. And so I think that space is leading in that sort of like exploration of like how do we leverage commercial networks of sensor data to improve basically the forecast for everyone, right? And this is, I think, broadly for land-based and ocean-based sensors is going to be something that we need to figure out together, because obviously there's a ton of benefit to it, but companies are paying for it. So somehow you need to figure out a model to make that shareable to everyone, because the benefits of that, like Julian pointed out, like sharing data broadly has always been so like prime driver to progress in global weather forecasting. And we're just in a new paradigm where models are going to be developed by small companies and data is going to be collected by small companies or big companies for that matter. And we need to figure out how do we unlock that data for the benefit of all.
Question on performance on extreme events. So we heard about having a benchmark for extreme events and like larger ensembles potentially like capturing the extreme events. I guess my question is, do we know why the AI models are going to do better on extreme events, and like how do we get those events to show up in the larger ensembles? Anyone know why?
Yeah.
I mean, it's just purely statistical at this point. If you have two models that are just as good in terms of deterministic forecasting, and you can generate a 50-member ensemble with one, then the likelihood of capturing something that's a 1 in 10,000 event is very low with a 50-member ensemble. But if you have a 10,000-member ensemble, there's a statistical chance that one of those 10,000 members will capture that event. So if you could generate a super large ensemble, you can start to sample the tails all the way up to 3 sigma, 4 sigma, 5 sigma, etc.
So can I ask you something? Because if you do 1,000 realizations and one of them happens to be right, like how do you know which one that is?
That is a great question. Yeah. So, which is why we use probabilistic metrics, right? So it's super low likelihood, but if it's sufficiently high risk, you might say that I might still want to plan for that one event that's 1 in 10,000 because the impacts are going to be so huge.
Yeah, so I think your point is made and proper. Like the fact that you can do 1,000 realizations gives you much better statistical band. So if the model is reasonably correct in its prediction of statistics, you're going to have a much better handle on the probability of occurrence. And then obviously it goes back to like how much data do you have of that specific event approaching hurricane? Like how much data can you feed in real time into a model to constrain it, to make that model more skillful? And then it depends on like how much compute can you throw at it, and how many sort of like realizations can you get to like reduce the statistics. So I think the advantage there is massive on the AI side.
I mean, my answer is right now we don't really know how good the models are at predicting extreme events. And there's been in each machine learning paper, we take a couple of case studies and we say, how did it do on this hurricane? How did it do on that event? And we have started to see some patterns, which is that it's better at hurricane tracks than it is on the intensities. And we wonder if that's around the goaling, the objective function of sort of the blurring and averaging statistical approach. But honestly, we need to do a lot more work to see how well these models are doing at lots of different events, and we're trying to push that with the extreme weather bench.
Back there.
Awesome. Taking the opportunity here that we have a mixture of startups and then large tech companies on the floor. Curious how you imagine those two different ecosystems coming together over time, and what's sort of better suited for Google or NVIDIA, and then for earlier stage companies. And any sort of collaboration conversations maybe underway or that you guys have contemplated?
I mean, I think I'd just like to say that the startups of today are the Googles of tomorrow, but
We'll just let Google buy all of us? No. Well, we collaborate with startups too. NVIDIA has been collaborating with startups for a fairly long time, and we've got a program where we work closely with startups on everything from the actual tech to bringing it out to market and so on. So I think there's a way to make it work.
Yeah, I think the reality is like we need everybody in this game. This is like really hard challenges, and everybody will bring something unique. And big company, small company, I think it's more like what can you bring to the table? Like for instance, we work with NVIDIA and MITRE to like bring together compute models and data. Where basically we're on the data side, MITRE is working on models, and NVIDIA is figuring out like how to actually run that efficiently on GPU. So it's hyper complementary, and I think the challenge is big enough to have like everybody in the room work together to advance. So I think the opportunity is massive there.
And actually, I would say in the audience, there's probably people with ideas on things that should be done in this space, and there is plenty of room. So you should go for it, because VCs seem willing to throw money at it right now.
I thought I'd just give a quick shout out to open source software, which I think is a really great way to sort of facilitate collaborations across organizations without, basically without getting any legal departments involved, just working on hard problems.
Echoing that, then another thing is bigger companies have more resources, but they also have had a lot of openness, which is great. So Google has done a lot of work with Weatherbench and open sourcing models. NVIDIA has always been like an incredibly helpful partner for startups. So it's definitely not like an or kind of thing. I think everyone can contribute. And yeah, I wouldn't think of it as competition. Even like very small teams can produce good results. If you look back on the history of deep learning weather forecasting, one of the first really, really promising results came from an individual researcher who I believe is at Brightband now. And that was always very inspiring. It's like you can just be a guy with a GPU and do like great results. So it's one thing where the way I think about deep learning in many ways is that one of the great things is that instead of requiring you to write down, every single differential equation, and, spend like, many PhDs, working on it, I'm not the smartest, guy. And like, all you have to do is put together a bunch of things and let the data learn. And so the fact that it enables relatively small teams, to have really expressive models, it allows them people like me to still like take part in this really fun field. So yeah.
Yeah, thank you for this great panel. I have two questions, so you can choose which one you prefer. So first question is, who is going to certify and also quantify uncertainty in several models? Like, for example, when we start from like a US government weather forecast, like we know it's US government, but if it's like one of your companies, like who is going to certify the uncertainty of the models? So first question, and second question is, if there are several models that are good, like if I want to use two of them, how can I do it? Like, do you think about interoperability, for example, for customers? Thank you.
I'll take your first question. I really like it. I actually think that that's a really good example of public-private partnership. I think, private companies will build forecasts and they do that for different reasons, for whatever drives them. I think a great role for the government would be like the arbitrator on electric quality in terms of like, hey, we have all these different forecasts. We are basically setting these metrics because we want to make sure that whatever goes to the public is of a certain level and they can depend on it. It doesn't mean like historically that they necessarily have to create that forecast. They can arbitrate basically other people's forecasts and set basically the level of accuracy and reliability they want to persist. So I think that is actually a really great opportunity. Like if you ask a company themselves, and I think this is the point you're getting at, we're going to be biased, right? We're not, not that we're trying to like mask anything, but we're going to probably find metrics that are probably, one, relevant for our customers, and two, showing that the model is actually really good because we put a lot of effort into it. And that's not intentionally sort of like misleading, but it is not the objectivity that a government would have in terms of like, setting standards around like what that could be. So I think it's an opportunity to work together. And it's, I think, also an opportunity to like set standards around it, because that's still the thing that I think we're not, just a discussion we had today around like, what are the right metrics, right? It's a hard question, not going to be easily solved. And I don't think anybody here will have an individual answer that's going to be agreeable to everyone. And I think that's where maybe a government agency could be incredibly helpful for it.
I think of the large language model market as a more mature AI market. And if you think about all the artifacts of that, some of the certification on metrics is done by organizations. You have the LLM Arena, leaderboard, which ranks different large language models. There's a ton of benchmarks. There's a lot of ways to have transparent evaluation. And so it could be government, but it could also not be government. I think the government will still have a role of putting out a forecast that they stand behind for a bunch of reasons. But let's think more broadly about, if we look at a more mature AI market, going from a world in which the government does everything, who's going to be the data layer? Who's going to provide the modeling layer? Who's going to provide the evaluation layer? There are all these opportunities for people to come together and add value in this space.
Maybe I'll briefly answer the second question about how to use these models together. And I think that's kind of the same way that we use like physics-based models, is that the best weather forecasts today are not from one model. They're from running sort of all the models, looking at the results, blending them together, sort of seeing if any, and different models have different strengths. And that's certainly true for AI models. And I think one organization that's really led here actually is, again, this ECWF, this European Weather Agency, that's now running the AI models, a bunch of different public AI models and their own physics-based model. And they're sort of sharing all those forecasts together. So you can kind of look at all the forecasts and make your own assessment of kind of what the most likely outcome is.
Is that on? Okay. Cool. So this has been amazingly enlightening, and I think you guys have touched mostly on short-term weather forecasting and performance there. So I wanted to ask what your perspective is on either one of two other forecasting objectives. One is just the climate scale forecasting. I think there's kind of obviously unique challenges there, given that the further out you go, by definition, the more out of sample we are. So I would imagine that presents different challenges to the AI forecasting world as compared to physics constrained, like more physics constrained models. And the second is I work more in climate risk. So like translating particular extreme events, but kind of all weather and climate events into different impacts. And we often use a lot of traditional statistical or econometric models for this. Are any of you working on like that stage of the translation piece from the physical side into impacts? And do you see any AI, any value to kind of the influence of AI there? I know that's kind of two questions, so you can just pick one area and go with it.
I mean, maybe I'll answer this. So these are both topics that I'm very interested in. My research team is spending a lot of time looking at right now. I think the hard thing about climate is validation. I mean, there are a lot of modeling problems too, but I think that we can figure those ones out. The hard part though is that you say you have a better climate model, and then how do you know it's actually a better climate model? We don't have any data from 50 years from now. So that's really hard. And also the climate modelers are actually a little resistant to write down a really clear set of metrics for exactly what it means to be a good climate model. It's a pretty hard question. It's there's a lot of, you have to get a lot of, not just predicting the right range of say temperature, the distributions. You have to get a lot of the physical mechanisms right in order to trust a climate model. So I think that's a challenge that the climate modeling field is sort of starting to embrace now. They've seen how powerful AI can be, but there is still a lot of resistance.